So this will be the first of a few videos that I make for Chem 111. And in each of these, we're going to be talking about some additional concepts that we talk about in class. The first of these, we'll be talking about derived units. So we've already talked a little bit about different kinds of units in the SI system. So let's review some of those. So we know that we have a few base units in the SI system. So for length, for instance, we know that we measure that in meters. And when I say that this is a base unit, what I mean is that this is our simplified set of units that all other units that we'll use will be derived from, or at least expressible in terms of. Okay? So for length, we know that we have meters. We've already talked about how for mass, we actually use the kilogram as our base, not the gram. So this is the only base unit that actually has an SI prefix at the beginning. Okay. But in either case, the base unit that we use here is the gram or kilogram. Okay. Here, meaning that mass is expressed in terms of some multiplier of grams. We also talked about how in the SI system, we use as our measure of temperature, we use the degree Kelvin, although we wouldn't say degree there. We would just write this as a Kelvin. Or the symbol for this can just be a capital K. Okay. Now, in addition to these three, the fourth one that would be relatively familiar for us is the unit for time. The base unit here is just the second, but we can also, we can express this in hours, minutes, etc. So that's just the ones that we're probably going to be the most used to here. The next one that we talked about, there we go, good enough. The next one we talked about was a measurement of the amount of a substance. And so here, what this was is we talked about a unit called the mole, right? And we know, for instance, let me switch colors here. I can also use my mouse for parts of this. We know that let me get rid of that 1 mole is equal to 6.022 times 10 to the 23rd of whatever that is. So if you have 1 mole of carbon atoms, you have that many carbon atoms, 6.022 times 10 to the 23rd carbon atoms. If you have 1 mole of water molecules, you have 6.022 times 10 to the 23rd water molecules. We will often call this Avogadro's number, or you may hear it called Avogadro's constant. But this is a common name that you'll hear for this, and it usually takes the symbol capital N sub A. Okay. So there's 2 more on our list that we'll go ahead and put in here. Although in this class, you're not likely to have to use these, but they probably will come up if you ever end up taking, say, a physics class. And this next one will probably be useful just in everyday life. These circles are not easy to draw with this tablet. So this next one is a measurement of electrical current. Right, and a lot of folks will probably have at least seen this before. This is the ampere. Right, we often just say amp, or we might use the symbol for it, which is just a capital A. Okay, and the last one that we have within our system of base units, and in fact, I should come up here and clarify that the units we're writing out here are actually SI base units. Because in a second here, we're going to be talking about some derived units. Right? These are going to be units that are made out of these other SI units. Let me just check. Okay, I just want to make sure that we're still good on that. The last one that I just want to talk about here is something called luminous intensity. You could think of this as just the amount of light that is being put off by some sort of light-emitting object. And here, what this is going to be measured in is a unit called the candela. Okay? So as I said, these last two may not be relevant for Chem 111. Let me make a note of that here. And feel free at any point while I'm writing these things down to skip ahead in the video. Okay. Now, we've talked about these base units here, but we're also going to have a number of units that are relevant to us in chemistry, physics, and even biology that may not be made directly of these units. So let's talk about one example here. I'm going to put derived units here just to distinguish these. And these are SI compatible in the sense that they're still part of the metric system. You can still express them as powers of 10 and use the SI prefixes for many of these. But they're not going to be part of our base units because we can actually express these in simpler terms. So let me give you a few examples here. For a first one, we can just look at something quite simple, area, right? We know that, for instance, if you're looking at an apartment or a home, your square footage is going to be the measure of the area of your apartment. So frequently you'll see this measured in square feet, right? But then we can also just think of this as feet squared. And this gives us an important insight here, that area has units expressed in the base unit system. It has units of length squared. So you might see square meters, you might see square centimeters, you might see square feet, right? But all of these are going to be measures of area because they all express it in terms of length squared. Now, of course, we also have other measures of area, right? We have acres, we also have hectares. But the idea here is that because we can actually express these as simpler quantities in terms of one of our base units, we don't consider acre or hectare or any of these ones like meters squared to be base units on their own. Okay, and in the same logic, we can talk about volume, and this will be relevant for the next one that we take a look at. Right? So if you're in nursing, for instance, or if you're in pre-med, you might know that a lot of times medicines will be measured in cc's, right? Of course, this is just going to be cubic centimeters. But then, of course, we could now see that, ignore some of these stray marks. We could just write this as centimeters cubed, which means that in general, we can say that volume has units of length cubed. Okay, so just as we talked about here, you might see things like cubic centimeters, you might see things like cubic feet, meters cubed, etc. We do have other things, right? We've got gallons, we've also got liters. And although these are also valid volume measurements, they're not going to be considered base units, right? Gallons here is part of the imperial system, so it's part of what we use here in the US, quarts, gallons, pints, etc. Liters, at least as a scientific measurement, would be more metric system in the sense that we generally wouldn't write something, right, like a milligallon. You know, we really don't say things like that, but we might say something like a milliliter, okay? So next, let's build on this idea of volume, right? Let's talk about density. Density, as we know intuitively, right, is how much stuff is just packed into a space, right? So we can think of that as amount of matter. We're just going to say amount of matter stuffed in a space. Actually, let's say stuffed in a given volume. right? Because now we might be able to start conceptualizing that this is essentially like saying amount of mass per a given amount of volume. Right? So if we think of one thing as having 1 gram of mass per 1 liter, right? That's going to be a lot less dense than something that has 100 grams of mass per 1 liter. So let me just write it as 1 gram per cubic centimeter, because this is the way that you'll often see this written, is less dense than 100 grams per centimeter, or cubic centimeter, excuse me. So with this written out now, we may have an idea of how this is going to look. We can say that density is going to have units of mass divided by, we could say volume here, okay, so let's go ahead and write that. But we can also write this as mass over length cubed, right? Just based on our definition of volume from before. And one way that you might see this written in some contexts, for instance, if you end up working in academic research, publishing papers, you might see length units written in this way, or density units written as mass length to the -3. So for instance, you might see grams centimeter -3, right? It's just a weird convention that you'll see sometimes, but it's good to be familiar with that. Don't be tripped up if you see it like that. You might also see velocity as like meters seconds to the -1, right? So to that point, let's talk about this. Let's talk about like speed and velocity for a second. So in a physics context, these two would not be exactly synonymous. But for us, for what we're doing right now, we don't really need to worry about that difference for what we're worrying about. What we should talk about here, however, is what is speed, right? It's how much distance you're covering in a given amount of time. Right? We often think of it as how fast we're going, but if we want to be precise about what fast means, we can say that speed is, let me fix that. Speed could be how far you go in a given amount of time. This tablet's a little funky because I have to look at the screen, but I got to move my hand over here on the tablet. So that's, and there's no visible screen on the tablet. So that's kind of an interesting writing experience here. Since I'm going to upload these documents later, I want to get this as clean as I can. So let me just fix that. No, I'm not obsessed with small details. What made you think that? Okay, so having said this, right, we can say that speed is going to have units of distance, right? But we would probably express distance in length. So it's going to have distance of length per time, or of course, you might see this as length times time to the -1. And if at any point these tablet notes get too illegible, we'll switch to just recording me handwriting something. I just figured no one wanted to stand up, stare at my hand that long. Okay, so on to the next one. We'll just do 2 more examples here. Let's, just in the same way that we built on area with volume, let's build on speed and velocity by talking about acceleration. Right? So what is acceleration? It's how much you speed up. In other words, how much your speed changes. So let me write it that way. In a given amount of time. And just so there's not these long pauses, you may see me use shorthand sometimes just to speed us along. Okay, so having defined it this way, right, what is a change of speed measured in, right? If you're going 15 miles an hour and you speed up to 20 miles an hour, the change in your speed is still going to be measured in miles per hour, right? It's a difference of 5 miles per hour. So what we can say is that acceleration is going to have units of change in speed, which is just going to be units of speed, units of velocity, right, which we now know is length per time. So let's write it this way. We're going to say that acceleration corresponds to a change in speed, which we know is length over time. And we're going to take all that, and we're going to say that's the amount that the speed changes per unit of time. So what we end up getting here, right, what we end up getting is length divided by time squared, meters per second squared, for instance. Here on Earth, right, the gravitational constant, the rate of acceleration of a falling object on Earth is about 9.8 meters per second squared, right? So if you've taken a physics class, you might have seen that number. That's not something you need to know here in Chem 111. But right, if you have taken that class, you might have seen that the rate of acceleration of an object falling on Earth is about 9.8 meters per second squared. I think it's like what, like about 22 or 32 feet per second squared, something like that. I'm just used to working in metric here. So one last example for derived units, okay? Let's now talk about one more concept that may not come up in this class until maybe later. But let's talk about force. So some of you may have seen Newton's second law before. This is the one that says that the force exerted on an object is equal to the mass times the acceleration of that object, right? So this might give us a clue. Since the units have to be the same on both sides of this might give us a clue of how to look at the units of force. So we know that if force is mass times acceleration, let's just write that out here. Let me make that an equal sign. So we have mass times acceleration. Right? Well, we know what the units of this are now. So we know that this would be units of mass. Right? I'm just going to copy this down where over here I'll note that, and it's a little late to note this, but square brackets here will be units. So we know that this is going to be units of mass, like kilograms, times units of acceleration. So for instance, let's write this out. We could say that this is kilograms times acceleration, let's say meters per second squared, right? Just like we see up here. So we're going to say that this is kilograms times meters per second squared, and in fact you'll usually see this written out like this. Right? But so this is going to be our units of force, where we're going to have that it's mass times length divided by time squared. And we're going to write that as, time with the squared outside of it, because it's the unit of time squared rather than the unit of parentheses time squared. If that makes any sense. If it doesn't, don't worry about it. So now we've talked a little bit about these derived units. One last thing I want to say about this is that there are a number of units that you will need to know. You'll just need to have these memorized, but these will also be quite helpful in everyday life, I think. Because most of these are ones that you see a lot of times in real life contexts. So for instance, here are the ones that you will need to know. And most of these will be useful in everyday life. There are maybe one or two that are not as much. That kind of looks like Hanno, doesn't it? So we have nano, and I'm going to write out the multiplier for each of these afterwards. We've got nano, micro, milli. We've also got, centi, deci. Also, we want you to know kilo, and I think it may only go up to mega. But I will also talk here about giga real quick. Any computery folks will probably already recognize some of these later ones, right? Kilobyte, megabyte, and gigabyte. The next one on, of course, would be terabyte. But giga is not one you'll necessarily need to know for this class. I just think it's useful to add that to the list because as computers become, as storage becomes cheaper, giga is an increasingly relevant one for a lot of folks. But these are the ones that you'll actually need to know for class. So let's talk about what these mean, and then let's briefly talk about what the connection between these and the units we're just talking about were. So these are all going to be prefixes that you put in front of a unit. And in this case, right, nano would mean that whatever unit you're putting this in front of, it's that times 10 to the minus 9. So for instance, 1 nanometer is equal to 1 meter times 10 to the minus 9. So it's a really small fraction of a meter. And we can do the same thing, right? If we just jump ahead, we can look at kilometer. Well, 1 kilometer would be 1 meter times 10 to the 3, the positive 3. Okay, we'll write that out when we get there. But this is how you use these. So just to fill out our table here, micro is a prefix that means 10 to the minus 6. Milli, we probably recognize this one. If not from an SI context like millimeter, then maybe from the context of like millipede, right? So the mil here meaning thousand actually, not million, but coming from the Latin where that would just mean thousand. Anyone who speaks Spanish in here would also probably recognize mil. So, and then it's the same with a lot of other Romance languages where mil would be the general idea of like 1,000. But where that's coming in here is 1 divided by 1,000. Or you could think of this as 1,000 millimeters is going to be equal to 1 meter. In other words, 10 to the positive 3 millimeters. Or we could write 1 millimeter equals 10 to the minus 3 meters. And then over here, actually, what I should also add is the prefix, or the abbreviation. So this one here is a lowercase n. For micro, you'll usually see this as the Greek letter u, the Greek letter mu. Sometimes you will see just a lowercase u. So let me move some stuff here. Oops. Should probably be a little more careful there. Okay, so let's move this over here because what I want to do is mark that you might also see this as a lowercase u. Good Lord. I'll just rewrite both of these. As I've said before, feel free to skip ahead to a place where I already have this fixed. So we have either a mu, or you might just see this as a lowercase u. Milli is pretty unambiguous. That one we just write a lowercase m. The next one we have on here is centi, where the abbreviation is just a lowercase c, like centimeters, cm. Next we have deci. So this one doesn't come up as much. You might recognize the prefix from like decimal, but we don't really use this one a ton. This would be 10 to the minus 1, and here it would just be a lowercase d. Now we get to the last few, which you probably will use. So a lowercase k, of course this is going to be kilo, and this is now where we have positive prefixes. So I'll just go ahead and write that just to be clear. Next we have mega, and this one uses a capital M. In fact, from here on out, the prefixes all use capital letters. This one is our prefix for 1,000. So, or I'm sorry, this is our prefix for 1,000,000. So that would be 10 to the 6. And then finally, for our list here, giga is going to be 1,000,000,000. So here we have 10 to the positive 9. Now, as I've said, you won't need to memorize giga for this class. Let me emphasize which ones. Okay. Last thing I want to do before wrapping up this video is just talk a little bit about unit conversions and how we would use these SI units in practice. So often, right, it's too cumbersome to write out all of these 10 to the minus whatever. So a lot of times, if you're just taking one measurement, you might use the relevant unit here. So if you, for instance, you're looking at a scale and you weigh something and you find out that this thing is 1,376 grams, right? But you don't want to write 1,376 every time. Actually, I guess it won't really be any shorter, but you want to put this in maybe a less cumbersome magnitude. Instead of around 1,000, we're just going to write this. We could write this, right, as 1.376 kilograms. But how do we just do that, right? Well, for me, that's just sort of muscle memory at this point. But let's look at what that process would look like. From our list above, we know what fraction of a kilogram 1 gram is. And we've talked about this a little bit in class where we've done things like, say, 1 mole of carbon atoms equals 12.011 grams of carbon, right? And that allows us to then divide each side by 12.011 grams of carbon, for instance. And then what we end up getting is what we call the molar, or the atomic weight, right? We say that 1, which is from this side here, so let me actually not complicate that. We say that 1 mole carbon atoms per 12.011 grams of carbon is equal to 1. And so we can take anything and multiply it by 1, right? And we're not changing the value. But by writing the 1 in this unique format, we can convert something from being expressed in terms of grams of carbon to being expressed in terms of moles of carbon atoms. Just in the same way that we can convert something expressed in feet to something expressed in inches or even centimeters without changing the amount of distance we're talking about. So it's going to be important for us to be able to set up what are called conversion factors. Let me separate this off for us. So let's write out a conversion factor. If I want to go from grams to kilograms, what I need to do is be able to write an expression like this one over here, right? Like this conversion factor here. We want to be able to write out one of these that goes from grams to kilograms. So what we can do here is we can say, well, what is the relationship between them to begin with? We know that if we find kilo on our list, that this is whatever amount of grams we're talking about times 10 to the third, right? So let's write that out. Let me get back up here. Just to make sure that that makes sense here, let's write it out like this, right? We can say that 1 kilogram, I don't know why I said it like that, 1 kilogram is going to be equal to 10 to the third times 1 gram. Right? Or in other words, just 1,000 grams. So what we can do is, now that we have this relationship set up where 1 kilogram equals, and I'm just going to write this now as 10 to the third grams, we can divide each side by either one of these. Well, which one do we want to divide by in this case? We start out with grams, so we're going to want to divide out that unit. Grams here is essentially in the numerator of an implied fraction. Right? We don't often write it this way, but just for the sake of thinking it that way, grams is in the numerator of this implied fraction here. So to cancel it out, just like if x were in the numerator of a fraction, we have to divide by that thing. Divide by x, divide by grams. So let's do that here. We're going to set up a factor, divide by the 10 to the third grams for each of these. And so these will cancel in our conversion factor. I'll switch colors here real quick. Right, so this gram cancels with this gram, this 1,000 cancels with this 1,000, and we're left with just 1. So what we can say is that we have a conversion factor that says 1 kilogram per 10 to the third grams equals 1. And we can multiply any amount of mass by this factor without changing the amount of mass that we're talking about, because these two are actually exactly equal. If you divide one by the other, you get 1. So let's see that in action. Okay. Ugh, this thing doesn't like finding my mouse when I also have the tablet attached here. So going back to our original number, 1376 grams, let's take this and multiply it by 1, right? This isn't going to change the value. This still equals 1376 grams. So now let's just re-express that 1 in the format we just wrote. Right? We just saw right here that we can write it in this format. So let's just copy that down here. 1376 grams times 1 kilogram divided by 10 to the third grams. And when I multiply this out, this is essentially taking this number, 1376, and dividing it by 1,000, right? But let's cancel our units real quick. So that cancels with that. We're just going to be left with kilograms. And 1376 divided by 10 to the third, well, that's going to be 1.376. And the only unit left over is going to be kilograms. Okay, let's look at one more example of that. And here what we're going to do is we're going to convert 2 in one step. So let's start off, instead of grams here, let's work in length. So we'll do centimeters to kilometers. Okay, so there's two things that we're going to want to note here. It's this 10 to the minus 2 and 10 to the plus 3. We're going to write out our equations to set up those conversion factors in just a sec down here. So we start out with a measurement of, let's get a new color here. We start out with a measurement of 100.6 centimeters. And we want to convert this into kilometers. Sorry, my K's are a little bit funky on this keyboard. Good Lord, that's just worse. Okay, so let's set up two conversion factor equations first. You don't have to do it this way, and in fact, we'll talk in a second about how you can bypass converting centimeters to meters and then meters to kilometers. But let's first just do it in 2 steps, okay? Just for the sake of getting the practice. So we know from our table above, we know that we would, if we're trying to get from centimeters to meters, we would take the number of centimeters and multiply it by 10 to the minus 2. Just like here, right? Here, what we're doing is we're taking the number of nanometers, 1 nanometer, and multiplying it by the conversion factor here, 1 meter times 10 to the minus 9. So let's come back down here, right, and we see that 1 centimeter equals 1 meter times 10 to the minus 2. So let's bring that down here. Ooh. Oh, good Lord. Okay. Okay, 10 to the minus 2, right? Or we can just get in the habit maybe of writing 10 to the minus 2 meters. Well, we can just take this and divide by either 1 centimeter or 10 to the minus 2 meters, and we'll have our conversion factor. But we know we're starting with centimeters. It's on the top of our implied fraction here, 100.6 centimeters divided by 1. So let's put centimeters on the bottom of our conversion factor. What we're going to do is we're going to divide this entire thing by 1 centimeter, and what we'll get is 1 equals 10 to the minus 2 meters divided by 1 centimeter. Now, some folks may be wondering, is it okay to take that 10 to the minus 2 and put that in the denominator? Yeah, absolutely, right? You can also write 1 meter over 100, or 10 to the positive 2 centimeters. So you're always welcome to do that. Whichever way of this makes more sense to you. The important thing here, though, is that we wanted to make sure centimeters was in the denominator here. So now when we take 100.6 centimeters, and we multiply that by 1 meter divided by 10 squared centimeters, so I'll just use this second format here. Now we're just going to get 1.006 centimeters, okay? Now we're not really worrying about significant figures in here, but let me make a quick point here. Some folks may see this 10 squared and say, does this limit our number of sig figs? And the answer is that no, in this case it doesn't, because whenever we have a number that we know is exact, for instance, 1 meter is defined to be 100 centimeters, or vice versa. You could say 100 centimeters is defined to be 1 meter, or 1 centimeter is defined to be 10 to the minus 2 meters, 0.01 meters. But because it's defined that way, that 100 is exact. Another example of this is that 1 inch is equal to exactly 2.54 centimeters. So if you have to convert something from inches to centimeters, the 2.54 in your conversion factor is not going to limit your precision because it's defined as exactly equal to that. There's no error in the precision of that multiplier. Okay. Oh, good Lord. So now we have, I was saying all that, and some folks will be looking at their screen saying, did you notice the error? No, I did now. Okay, right? Oh, come on, just move it over. So now we've converted this from centimeters into meters, because we can see that centimeters here will cancel. But our goal was to go to kilometers, right? This is what we really want to do. So now we still have to take this and say, how many kilometers? Well, let's scroll back up, refresh our memory. Kilo here on our list has a multiplier of 10 to the plus 3. So 1 kilometer would be 10 to the plus 3 meters. So now that we're here, let's switch over to red, and we'll write out our new conversion factor. 1 kilometer equals 10 to the plus 3 meters. Okay? So we can say, let's go ahead, and in this case we're trying to get rid of meters. And we're trying to go 2 kilometers. Now meters is on the top of this implied fraction, 1.006 meters divided by 1. So let's take it and we'll copy it down here, and for the sake of this example I'll write out the fraction that way. I don't usually write it out this way, and I know some folks like this and some folks find it more confusing, so just pick whichever one you're more comfortable with. But I'm going to write it this way to emphasize to myself that the number of meters is on the top. So when I write out my conversion factor, what I'm looking for is 1 kilometer divided by 10 to the 3 meters. Okay, so now what I get, let's go pick one last color. So meters will cancel, and now I'm left with 1.006 divided by 1,000. I'm just going to write that actually as 1.006 times 10 to the minus 3, right? And the minus, we pick up the minus here because our 3 was in the denominator. So, and our units here are just going to be kilometers. So by going through it this way, what we've seen, let me pick one last, we'll go back to black here. What we've seen is that our original number of 100.6 centimeters is going to be equal to 1.006 times 10 to the minus 3 kilometers. Right? And if we were worried about sig figs here, we retain all 4 of them here, because along the way, the only thing we've done is use exact conversion factors, which have effectively unlimited sig figs. Okay. So you can take any of these prefixes that you see in this table here, and you can apply them to any of these base units and most of these derived units. Right? As I mentioned, we wouldn't say kilogallons or milligallons. There are a few imperial units, like PSI, for instance. If you ever work on like air gauges and stuff, you might see KPSI or MPSI. Sometimes those are pronounced as kips, actually. And that's like kilo PSI, thousands of pounds per square inch. We didn't really talk about pressure in here. It's another derived unit that we may get to at one point. But the reason I bring that up here is to say that most of these derived units can also be expressed with SI prefixes. So like you see here, you could have cubic centimeters, right? And you don't just have to have cubic meters, but you can express something in cubic centimeters. Maybe we should do one last example here just to show how things look when you're working with something that is cubed or squared. So let's do one last simple example. I would challenge you later to try one with, you know what, screw it. Let's just do one example with density, okay? So we're going to start out with a measurement. Where is my mouse? Let's start out with a measurement that's 13.6 kilograms per meter cubed. And we want to take this and go to grams per cubic centimeter. Okay, so you see that we've got 2 conversions here. We're going to need to convert the mass, and we're going to need to convert the volume. Let's do this all in one step. So what we're going to do is we're going to write out our equation here. Fortunately, at this point, I think we're familiar with kilo and centi, right? But I'll write out those conversion factors and talk about them as we get there. So I'm going to write this actually this way. I'm going to write it as 13.6 kilograms per 1 meter cubed, right? You don't have to do it this way. You could just write it as 13.6 kilograms per meters cubed. I'm just choosing to make the fraction bar that you see in kilograms per meter cubed to make it very explicit for us. Because by doing it that way, we can keep it super clear what's trying to be canceled with what. Let's write our first conversion factor here in red. So we're going to get rid of the kilograms here. Well, let's write it this way. Let's start out here. We know we want to go from kilograms to grams, right? I think I made that K worse. Well, we need a relationship between kilograms and grams. We can go back up to our table and see that kilo is 10 to the plus 3, meaning that 1 kilometer equals 10 to the plus 3 meters. So 1 kilogram is going to be 10 to the plus 3 grams. All right, easy enough. So we'll go ahead and write that in here. Now, of course, you might have chosen to write that as 10 to the minus 3 kilograms equals 1 gram, and that's also okay. This one just makes a little bit more sense to me. I like to think in terms of one of the bigger unit is how many of the smaller unit. But there's a lot of ways you could write that, and they're probably all equal. I just have to see the specific one, you know. So let's write this next one in blue. What we're going to be careful about here, right, we're going to try and get rid of this meters cubed and make it centimeters cubed. The important thing to note here is we're going to set up a conversion factor from meters to centimeters and cube the whole dang thing. Okay, so let's just write this in here. On top we're going to put 1 meter, and on the top we're going to put meters. Right, we'll figure out the number in a sec. And we're going to take this whole thing and we're going to cube it. Now, the way I like to think about this is one of the big units, so 1 meter, is how many of the small unit? It's going to be 10 squared, 100 centimeters, right? So you could say that 1 centimeter equals 10 to the minus 2 meters. That would have 1 on the bottom and the factor of 10 on the top. But we're going to write it this way. And again, either one is okay with me. Just make sure you get the magnitude of the exponent right. Okay, so if we take this, and I'm actually I wanted to write my equal sign in orange with the rest of our equation. So let's get rid of that. So we can actually see that this second factor winds up being not 10 squared, right? Where is my, there we go. It's not 10 squared, or 1 over 10 squared rather, but it's 1 over 10 squared cubed. So what we're going to do is I'm actually just going to put this into a calculator after I've canceled out some units. Let's do our unit calculation in black. So kilograms here will cancel with kilograms. Meters cubed, right, is going to cancel with meters after it's cubed. So we can go ahead and cross that off and just know that that meter will become meters cubed once we expand out this whole thing. And with that, let me just go ahead. Actually, we can, let's take this second term here and just multiply this out so it's a little bit easier for us to put in the calculator. We can write this out now as 1, right? No meters cubed, because that part we've already canceled. So 1 divided by, well, 10 squared cubed is going to be 10 to the 6th. So that's going to be 10 to the 6th cubic centimeters. This is our cc's that you might have heard of. So 10 to the 3rd divided by 10 to the 6th is 1 over 10 to the 3rd. So what we get is, I'm going to write it this way first, 13.6 grams divided by 10 to the 3rd centimeters cubed. But the way that we're going to finish writing this is let's not worry about adjusting the scientific notation. 13.6 times 10 to the minus 3 grams per centimeter cubed. Okay? And we could choose, right, we could make this 1.36, right? So what did we do? We divided this bit, we divided 13.6 times 10. So to keep it the same size, let's also multiply it by 10. So that could be times 10 to the minus 2, right? Essentially 13.6 divided by 10 times 10 times 10 to the minus 3. And the 10s in the second bit, the second group, cancel out. And if that's all confusing, then hey, you can also set up, you can take more time on those scientific notation ones, but I'm honestly fine with 13.6 times 10 to the minus 3. Okay? So in this case, both of these would be fine with me. But you see how we started out with something in kilograms per meter cubed, and to get rid of the meters cubed bit, we really had to come in here and be careful to cube the entire conversion factor. Okay? So this is a little primer on derived units and base units. I'm going to take this and upload this. This will be the first of our little modules. And after this, I will move on and talk a little bit about accuracy and precision. Thanks for watching.